Welcome back, probability students. This is the third video in our assignment series. Today we'll tackle parameter estimation, or how to fit a theoretical distribution to an empirical distribution. If you're here, you should already have code that loads a data set, computes some elementary descriptive statistics, and creates some data visualizations. Your code should also create an empirical distribution from your data set. Moving on to what's new in this example, I'll estimate the total size of a rabbit population as well as the size of a subcategory of rabbits with tularemia. These are both parameters of a hypergeometric distribution. I'll use the mark and recapture method coupled with the method of moments in order to accomplish this. This is different from what you'll do if you are working with the binomial, geometric, or Poisson's distribution, so I'll provide instruction for working with these distributions in a separate video. To employ mark and recapture, I'll begin by estimating the total rabbit population, or capital N. To do so, imagine capturing k sub 0 equals 100 rabbits, tagging them, and then re-releasing them. Then in succession, capture 8 samples of lowercase n equals 30 rabbits each, and record the numbers of tagged rabbits found in each sample before re-releasing them. This results in a data set I've labeled X captures. I then use the method of moments formula, or total population is approximately equal to the sample size times the size of the captured population, tagged population, divided by the mean of the recently collected data set to estimate the total population. Since this is an integer population size, I round this result. Now that I have an estimate for the total population size, I can use the method of moments on my original data set to estimate the size k of the infected population of rabbits. The result of this process are estimated values of n equals 1,412 for the total population and k equals 448 for the infected population. A natural question to ask is, how good are these estimates? One way to address this question is to compare the theoretical hypergeometric distribution calibrated with my estimated parameters to the empirical distribution using graphical means. The displayed code accomplishes just that. You might notice that the first several lines of code are simply a repeat of the code used for constructing the empirical distribution in assignment 2. What's new here is that we superimpose a bar graph of the theoretical distribution onto the empirical histogram. The result of this is the displayed graph. The results look very similar. This is one indication of a good fit. Another comparison that we can make is to see how close the empirical shape parameters of our data are to the corresponding shape parameters of the theoretical distribution. This code makes just such a comparison of the mean, variance, skewness, and kurtosis for the hypergeometric distribution and displays the results in a table. As you can see, the results are fairly close once again. This is another indication of a good fit. We'll explore one more technique for validating our fit in our assignment 4 video.